This is our third video lecture for Chapter 17, and we begin our discussion with the third law of thermodynamics and talking about absolute entropy. The absolute entropy of a substance is the amount of energy it has due to dispersion of energy throughout its particles. The third law states that for a perfect crystal at absolute zero, the absolute entropy equals 0 joules per mole K. So a perfect crystal is a crystal that's perfectly ordered. There's no defects in the crystal structure and everything's nice and neatly organized. So this would be an example of a perfect crystal. Everything's neatly stacked and organized and there's nothing missing and things aren't shifted. Everything's in a nice organized pattern. So every substance that is not a perfect crystal at absolute zero has some energy from the entropy. Therefore, the absolute entropy of a substance is always positive. Standard entropies are represented by capital S, and these are extensive properties. And these entropies are for 1 mole at 298 K for a particular state, a particular allotrope, a particular molecular complexity, a particular molar mass, and a particular degree of dissolution. So for example, this is a table of entropy values. So notice that carbon and graphite, these are allotropes of each other. So it's the same element, they're just arranged differently, the atoms are. So there are sheets of carbon in the graphite, and in the diamond all the carbons are tetrahedrally bound. So notice that there's a difference in the entropy even though it's both carbon, it's just their allotropes are different. So the diamond has a smaller entropy value than the graphite. Also, this state is going to play a factor. So look at the entropy of water in the gaseous state, that's 188.83, whereas in the liquid state we expect the entropy to be lower. So it has a value of 69.91. So the entropy is dependent upon the particular compound and the state it's in and some of those other factors that we discussed on the previous slide. The gas state has a larger entropy than a liquid state at a particular temperature. And we said this was due to the more arrangements and the more movements that the gas particles can have compared to the liquid state. The liquid state has a larger entropy than the solid state at a particular temperature. Again, there's more freedom of motion and movement for the liquid than there is in the solid state. So just comparing the water in the liquid form versus the gaseous form. So the gaseous form, we'd expect there to be more entropy because there's more space between the water molecules and there's more room for them to spread out, and there's more arrangements that you can have in the gaseous state than in the liquid state. Now the larger the molar mass, the larger the entropy as well. So notice that we're looking at helium, neon, argon, krypton, and xenon. These are the noble gases. And these are all monatomic gases, and helium is the smallest. We have pictures here to show the relative sizes. And helium, the smallest, has the smallest entropy. But as you increase the radius, so you're increasing the size of the atom, the entropy also increases. So available energy states are more closely spaced. This allows more dispersal of the energy throughout those states. Here we're comparing the relative standard entropies of allotropes. So remember we were talking earlier about the entropy of diamond versus graphite. We said that the diamonds were all tetrahedrally bound, so they're all linked to each other with carbon-carbon bonds. But in graphite, notice there's only intermolecular forces here. We don't show any covalent bonds in between these layers, and these layers can slide past each other, which gives graphite its slipperiness and why it's used as a lubricant. So because you can slide these past each other, this is going to have more entropy. You can have different ways of arranging the graphite. So the entropy of graphite is 5.7, which is higher than the diamond at 2.4. So what we can glean from this example is the less constrained the structure of an allotrope is, the larger its entropy. And here we're looking at more complex molecules. Larger, more complex molecules generally have larger entropy. More available states allows more dispersal of energy throughout those states. So if we're looking at argon, remember argon is a monatomic gas and its molar mass is 39.94. But NO is another gas, but it's a diatomic gas, and it actually has a smaller molar mass than argon. But the entropy is larger than that for argon. So the entropy of NO is larger for the argon, and this is because of the different ways that the nitrogen and oxygen molecules can be oriented when determining the entropy. So there are more states available. So just like the argon, the NO can have translational motion. But with the NO, you can also have rotational motion. So spinning it around and having the red on one side and blue on the other, that's a different state. Also with the NO, because you have a bond in between the nitrogen and oxygen, you can have vibrational motion. So you can imagine these two springing into each other and stretching out and compressing. And so everywhere along this line, the potential distance between those, you have different states that the NO can be in, and this contributes to its higher entropy value than with argon, which is a single atom. Now, when comparing solids to aqueous solutions, dissolved solids generally have larger entropy. This is because you're distributing particles throughout the mixture. So for this sample of potassium chlorate, in the solid state, it's 143.1, but dissolving that up and breaking it up into the K plus and the ClO3 minus, that entropy value is now 265.7. In this problem, we're going to calculate the delta S for the reaction. So we've got ammonia combining with oxygen to make NO and water. These standard entropy values, you can find these in the appendices in the back of your book. I've listed them here in the table for you. So using these entropy values for the individual substances, we can find the delta S, or the change in entropy for the entire reaction. So to find the change in entropy for the reaction, we're going to use the sum of the entropies of the products and subtract out the sum of the entropies for the reactants. So using my balanced chemical equation, there are 4 NOs, and each NO has an entropy of 210.8, so 4 times 2, 10.8. There are 6 water molecules. The water value is 188.8. So we sum this together, and then we're going to subtract out the sum of the entropies for the reactants. So this 4 comes from the fact that there are 4 ammonias at 192.8 apiece, and there are 5 oxygens. Each oxygen is 205.2 joules per Kelvin. So when we put this into our calculator, we should get a value of 178.8 joules per Kelvin. And this is a positive change in entropy. And this is what you would expect for a reaction with more gas product molecules than reactant molecules. So we have 10 equivalents of gas molecules as products, 9 as reactants. So we have more molecules of gas as the reaction progresses. So we should have more entropy, and more entropy means a positive delta S value. Now let's look at calculating the Gibbs free energy, or the change in the Gibbs free energy at standard conditions. So at 25 degrees C, summing the delta G for a reaction is very similar to summing the delta H of a reaction, or delta S. So the delta G for the reaction is the sum of the Gibbs free energies for the products minus the sum of the Gibbs free energies for the reactants. But the values listed in the books are at 25 degrees C. If we want to use a temperature other than 25 degrees C, we use the relationship that delta G equals delta H minus T delta S. And to use this, we're assuming that the change in the enthalpy and the change in the entropy is negligible by changing the temperature. So again, the delta G values for the individual elements and compounds, you can find these in the tables and the appendices in the back of your book. So let's look at calculating the delta G of a reaction using the table values for the products and the reactants. Here we're combusting methane, so we're combining oxygen and methane to produce carbon dioxide, water, and ozone. So using the delta G's of the products and the reactants, we're going to find the delta G of the reaction. So for CO2, it's negative 394.4, and there's only one CO2 in our balanced chemical equation. There are two water molecules, and the water molecule is negative 228.6. plus 4 times that for the ozone, so 163.2. So we'd sum up this portion of our equation, and then we're going to subtract out the sum of the delta G's for the reactants. So there's one methane, and methane is negative 50.5. There are 8 oxygens, and oxygen here, the oxygen is in its standard state condition. It's gaseous, so it's 0. So negative of a negative is a positive. So we add that 50.5 kilojoules to our sum here. And when we put this in our calculator, we should get a value of negative 148.3 kilojoules. This is the delta G for the reaction at 25 degrees C for this combustion of methane and oxygen. Now let's go back and look at determining the delta G at a temperature other than 25 degrees C. So here in this reaction, we're given that sulfur dioxide combining with oxygen will produce sulfur trioxide. They've given us the delta H as negative 98.9 kilojoules and the delta S, so the change in entropy, as negative 94.0 joules K at 25 degrees C. They want us to calculate the delta G at 125 and determine if it's spontaneous. So I've listed the values that I've been given, the delta H, the delta S, and the T. We want to find the delta G from those values, so we can use the equation delta G equals delta H minus T delta S. So I substitute in my delta H value. Here I've converted it into joules from kilojoules. My temperature needs to be in Kelvin, so at 125 plus 273 gives me 398 Kelvin, times the change in entropy, so times negative 94.0. When I put this into my calculator, I should get negative 61.5 times 10 to the third joules, which would be the same thing as negative 61.5 kilojoules. So this would be the delta G for this reaction at 125 degrees Celsius. Since the delta G is negative, the reaction is spontaneous at this temperature, though it's less spontaneous than it would be at 25 degrees C. Now there are some relationships that we can use for the delta G. If a reaction can be expressed as a series of reactants, the sum of the delta G values of the individual reaction is the delta G of the total reaction. So just like Hess's law, when we could sum up the delta H's of reactions to get the overall reaction, we can do this for the delta G as well. And this is because the delta G is a state function. It doesn't matter how you got there. They just want to know what it is compared to what it was. So it's a state function. If a reaction is reversed, then the sign of the delta G value is also going to be reversed. If we multiply through by a factor, so if the amount of materials is multiplied by a factor, the value of the delta G is multiplied by that same factor. And this is because the value of the delta G is an extensive property. So it matters on how much is there. Sometimes we want to find delta G under non-standard conditions. But delta G will be equal to the delta G at standard conditions only when the reactants and products are in their standard states. This is their normal state at that temperature. For example, you would find oxygen at standard condition to be in the gaseous form. You would find graphite, which is an allotrope of carbon, in the solid form at normal temperatures and pressures. And then the standard states are also the partial pressure of a gas at 1 atmosphere and the concentration as 1 molar. But when we want to use non-standard conditions, the delta G of reaction is related to the delta G at standard conditions plus RT ln of Q, where Q is the reaction quotient that we saw when we were studying equilibriums. So it's still the products over the reactants, but it's just not at equilibrium. Now we said that when delta G equals 0, this is when we have an equilibrium. Well, if delta G equals 0 at equilibrium, we can rewrite this equation above, so 0 equals negative delta G plus RT ln of Q. So 0 equals delta G naught plus RT, and we said we're at equilibrium, so rather than writing ln of Q, we can write the ln of K. So if I isolate the delta G by itself, delta G equals negative RT ln of K. Here we have a reaction of water in the liquid form going to water in the gaseous form. So we're starting off with all the water in the liquid phase, and the Q is going to be 0 because we have no products yet. And on the y-axis we've got free energy. On the x-axis we have the partial pressure of the water. So remember, this would be the pressure of the gaseous or the vaporized water. So at 0 atmospheres we have no water vapor. But as the reaction progresses and we start approaching equilibrium, going in this direction we have a decrease in the free energy. So if the free energy is decreasing, we have a negative change in the delta G. So our delta G is negative as we go down. Now once we get to the bottom of this well, we reach equilibrium. So at equilibrium the delta G equals 0 and the Q, the reaction quotient, equals K. But if I keep progressing with this reaction and keep going and pushing the reaction so that there's more water vapor, then the Q is larger than the K. And if I keep going up the hill, the reaction is not going to be spontaneous. And so the delta G is positive going up. So going up, we have a delta G that's positive. So to do the reaction in the spontaneous direction, so going in the reverse, when you've got too much water in the gaseous phase and some needs to condense, going back down this hill in the opposite direction, because now we're reversing the reaction. You can almost think of this arrow representing the water in the gaseous phase going to the water in the liquid phase. So going in this direction, it's delta G is negative, so it's spontaneous. As I keep going up, go past the equilibrium and keep going up the hill, the delta G is positive and the reaction is non-spontaneous. But it will eventually condense if I go back where it's a negative delta G going in this direction. And if I go past the equilibrium and go up this side, then it becomes positive and the reaction is no longer spontaneous as well. So the reaction wants to move towards wherever this minimum value is in free energy to reach that equilibrium. Here we have an example where they want us to calculate the delta G at 427 degrees Celsius for the reaction below where we're combining nitrogen and hydrogen to make ammonia gas. So we're going to use some of the equations that we looked at before where we relate the delta G to the delta G at standard conditions plus the RT ln of Q. And we're going to use the relationship that delta G equals delta H minus T delta S. So to start this reaction, I first want to find my Q value. So I have my reaction here, but we're not at equilibrium. So my products over my reactants with the pressure of my NH3 squared over my nitrogen pressure and my pressure of my hydrogen cubed. So I plug in my values and I get a Q value of 1.2 times 10 to the minus 7th. So now that I've got my Q value, so I've got this part of my reaction and we want to find the delta G. And remember, we want the delta G at a temperature other than standard conditions and not at equilibrium. So I need to be able to find the delta G naught. To find the delta G naught, I'm going to use the equation where delta G equals delta H minus T delta S. So I find my delta H by using the sum of the delta H's of the products minus the sum of the delta H's of the reactants to find my delta H of the reaction at standard conditions. And notice here that we have nitrogen at its standard conditions, so it's a gas. Hydrogen's at standard conditions, so those gases at those standard conditions, the delta H is 0. Those delta H's of formation are 0. Then I'm going to find my delta S, the change in entropy for the reaction. And these values that I've put in, these are values that I've looked up in a table in the appendices. So 2 times the ammonia entropy minus the entropy for nitrogen and the entropy for 3 hydrogens. So the delta S for this reaction is negative 198.2. Notice we have a decrease in the entropy. It's a negative value. This is what we'd expect for going from 4 moles of gas to 2 moles of gas. So now that I have my delta H and delta S values, I can plug those in to find my delta G from my equation delta G equals delta H minus T delta S. I had found that my delta H was negative 92,380 joules minus the temperature. So the temperature that we're interested in is 427 Celsius. I have to add 273 to get the Kelvin, so 700 Kelvin, times the entropy of the reaction, so times a negative 198.2. This gives me a delta G at standard conditions of 46,400 joules. I now have my delta G naught. R is a gas constant, and T is the temperature that we're interested in. So I can plug in my values into that equation, and I get a delta G for the reaction at those conditions as being negative 46 kilojoules. Here we've got 3 different reactions. In this first one, where we have A going to B, we have an equilibrium constant of less than 1. So because the equilibrium is less than 1, the reaction lies more towards the reactants. The second one, we've got a reaction where the K is larger than 1. So in this one, the equilibrium lies to the right, where there are more products than there are reactants. And in case C, we have a K value of 1, so the equilibrium constant is 1, so there are equal amounts of the products over the reactants. And at these graphs, we're looking at how the reaction changes to where we are in the reaction. So if we're looking at this blue line here, that you have a value on the free energy axis, but it's not at the minimum of this energy well. So the reaction is going to proceed to reach that bottom. So the reaction is actually going to reverse here. So here at these standard conditions, where the pressure of A and the pressure in B are at 1 atmosphere, we have a Q value of 1, so it'd be 1 over 1. So if the Q value is 1, the reaction is going to be spontaneous in the reverse direction, because we have to get that Q value closer to whatever our K value is, and we said that K is less than 1, so it's going to have to go in the opposite direction. It's going to have to go in the reverse for it to be spontaneous. Now here in case B, where we also have standard conditions at this blue line, we have a Q value of 1. Well, if K is larger than 1, the reaction is going to have to proceed to get towards that minimum, so it's going to have to go in the forward direction. So the reaction is going to have to shift to make more products to reach that equilibrium value. But here where K equals 1 in figure C, so Q equals 1 as well, the reaction's already at equilibrium. So to either go in the forward direction or the reverse would be non-spontaneous, because it'd have to go up the hill in either direction it goes. So it's not going to want to do anything. It's going to stay at equilibrium. Here we want to estimate the equilibrium constant and position of equilibrium for the following reaction. Again, we're looking at nitrogen and hydrogen combining together to make ammonia. And I've just transferred some of the information from the previous slide. So the delta H, where we did the sum of the delta H's for the products minus that of the reactants. The delta S is again, so the sum of the products entropies minus the sum of the entropies for the reactants to get the overall change in entropy for the reactants. And we said that the delta G at these conditions was 36,400 joules. Using delta G naught equals RT of ln and K, so this is at equilibrium, because they tell us in this reaction that they want to estimate the equilibrium constant for the equilibrium. So if we've got an equilibrium, we use the equation delta G equals negative RT ln and K. I substitute in my delta G value as being 46,400 joules. R is my gas constant. T is the temperature that I'm interested in. So we're interested in what's the equilibrium constant at 427 degrees Celsius. So we add 273 to get a Kelvin value of 700. And we'll solve for the ln of K. The ln of K equals negative 7.97. I need to find what K is. Since we are using the natural log, the ln, this would be e raised to the negative 7.97 to find the K. So K equals e raised to the negative 7.97, which gives us a value of 3.45 times 10 to the minus fourth. So this would be the equilibrium constant that we would predict for a temperature of 427 for the nitrogen and hydrogen combining together to make ammonia. Since the K is less than 1, the position of the equilibrium favors the reactant, so it favors the reactant side. So in the previous slide, we were calculating the equilibrium constant at a different temperature. There's a temperature dependence of the equilibrium constant, and we can use a graphical relationship to see this. Here I'm starting off with my delta G equals negative RT ln K for an equilibrium system, and our equation where delta G equals delta H minus T delta S. If I combine these two reactions, so I have delta G in both portions, I'm just going to set these two equal to each other. Now if I divide both sides through by negative RT, so that cancels out, and my temperatures here cancel out, I can get the equation in the form of ln of K equals negative delta H over R times the inverse of temperature plus delta S over R. You may wonder why I'm pulling out the T and having it 1 over T multiply this. If you look at this equation, hopefully you see something familiar. This should look like the equation of a line, where the ln of K is the y value, negative delta H over R is the m value. This would be the slope. You can plot the inverse temperature, and the y-intercept would be the delta S divided by the gas constant. So in lab, you will actually be determining the equilibrium constant at different temperatures for the dissolution of barium iodate. And you will be plotting the ln of the K value versus the inverse temperature. So from the slope of the line, you will be able to determine the negative delta H, because the negative delta H over R is going to be your slope value. And from the intercept, you can get the delta S. So if you multiply your intercept value times the gas constant, you can get your entropy of the reaction. And if you multiply your slope by the gas constant and times a negative 1, you can get the delta H of the reaction. For an exothermic reaction, so an exothermic reaction would be a delta H, where you have a withdrawal of an energy, so it's a negative. If we're looking at our equation for our line, a negative times a negative would give us a positive slope. So for an exothermic reaction, you should have a line like this where the ln of K is increasing as the 1 over T increases. So the slope of the line should be positive. Whereas with an endothermic reaction, so an endothermic reaction, remember, is a delta H is positive. So if the delta H is positive, positive times a negative, you should get a negative slope when you plot the ln of K versus inverse temperature. So increasing the temperature of an exothermic, so let's say we have our reactants going to our products, and heat would be a product. Increasing the heat should cause the reaction to shift to the left to produce more reactants, so the K value will get smaller. Whereas when heat is a reactant, increasing the heat should push it towards more products. This will increase the K value, so you will have a positive slope. In summary, for an exothermic reaction, increasing the temperature decreases the value of the equilibrium constant. K gets smaller. For an endothermic reaction, increasing the temperature increases the value of the equilibrium constant. This concludes our video lectures for Chapter 17, Thermodynamics.